Today's lesson is on empirical rule. It's going to take what we learned about on the standard normal distribution and start looking at how we can generalize it to normal distributions. So a normal distribution is similar to the standard normal distribution in that it still describes a bell-shaped curve. The peak is still at the middle and it's still the mean, but the mean could be any value, not necessarily 0. Okay. The normal curve is symmetric. Okay. 50% of the area is still to the left of the center, 50% is still to the right of the center. The normal distribution curve still approaches the x-axis and gets closer and closer but never touches it, but we do tend to label with just a normal curve the x-axis with the x variable. It's not a z-score anymore. Doesn't have its center at 0 anymore. Okay. So when it comes to understanding this curve, what controls how spread out it is how big the standard deviation is. We can still label the x-axis with standard deviation. To the left, we're 1 standard deviation, 2 standard deviations, or 3 standard deviations below the mean. And to the right, we're 1 standard deviation, 2 standard deviations, or 3 standard deviations above the mean. Okay. The value of the standard deviation controls how quickly the normal distribution approaches the x-axis. If the standard deviation is larger, then the curve will be flatter. It'll be more spread out. If the standard deviation is smaller, then the curve will be less peaked. So the difference is a large standard deviation means that my curve is fairly flat. A small standard deviation means that my curve is more peaked because we will go from our mean to our 3 standard deviations much quicker. And remember, the cumulative area underneath the curve is always 1. So our first generalization before we go to tomorrow's lesson, where we're actually going to be converting our x values into z-scores, is we're going to look at a generalization that helps us ballpark estimates, and that's the empirical rule. So how the empirical works is that between 1 standard deviation of the mean, and I'm sorry, this image isn't really well centered, but between 1 standard deviation of the mean, we always have this middle 68% of the data represented. So if we want to know where the middle 68% are, we can get the lower value by taking the mean minus 1 standard deviation, and we can get the upper value by taking the mean and adding 1 standard deviation to it. Okay. Moving further from that, we can get the middle 95% of the data by moving 2 standard deviations for the mean. So the lower limit is the mean minus 2 standard deviations, and the upper limit is the mean plus 2 standard deviations. Finally, our third part of the empirical rule tells us that if we move 3 standard deviations from the mean on either side, we get the middle 99.7% of the data represented. So we find the lower limit by taking the mean and subtracting 3 standard deviations. And we can find the upper limit for that range by taking the mean and adding 3 standard deviations. Okay. That rule is summarized on the following pages. You might want to put it on your formula sheets for the final test. Let's look at a few examples. So, a word problem. The New York Times reported that the average high temperature in San Francisco in January is 55 degrees Fahrenheit. That means our mean value is 55 degrees Fahrenheit, average value, and the standard deviation is 3 degrees Fahrenheit. The distribution of these temperatures is symmetric and bell-shaped. Using the empirical rule, determine the range of the high temperatures that would include about 68% of the January days. So to do this, since we're finding 68%, we're going to move one standard deviation from our mean. So our lower limit is going to be the mean value minus one standard deviation. That gives us a value of 52 degrees Fahrenheit. Our upper value is 55 degrees Fahrenheit plus one standard deviation. That gives us a value of 58 degrees Fahrenheit. So therefore, 68% of the January days would be between 52 degrees Fahrenheit and 58 degrees Fahrenheit. If we change the question to ask what range of temperatures would include about 95% of the January days, then since we're going to 95% by empirical rule, that means we have to move 2 standard deviations from our mean. Our lower limit value would be 55 degrees Fahrenheit minus 2 standard deviations, right? 55 minus 6 is 49 degrees Fahrenheit. And our upper limit would be our mean plus 2 standard deviations. Don't forget to use your order of operations. Multiplication first. 2 times 3 is 6. Plus 55 is 61 degrees Fahrenheit. Therefore, 95% of the days would be between 49 degrees Fahrenheit and 61 degrees Fahrenheit. The third part, part C of this question, asks for the range of temperatures that would include 99.7% of the January days. 99.7% corresponds to 3 standard deviations from the mean according to empirical rule. So the lower limit would be the mean minus 3 standard deviations, which would give us a lower value of 46 degrees Fahrenheit. The upper value is the mean plus 3 standard deviations. That would give us an upper range of 64 degrees Fahrenheit, and therefore 99.7% of the days would be between 46 degrees Fahrenheit and 64 degrees Fahrenheit. Okay. For other questions, again, we have to pay attention to what percent range we're being asked to find, and then make sure we extract the correct information about the mean and standard deviation. Let's look at the second example. The weights of 10-year-old children approximate a bell-shaped or normal distribution. The empirical rule can be used to estimate the ranges of weights. The mean weight is 65 pounds, and the standard deviation is 10 pounds. About 68% of the children would be expected to have a weight of how many pounds? Again, 68%, that means we're 1 standard deviation from the mean. So our lower limit is the mean minus 1 standard deviation, so that would be 55 pounds. The upper limit is the mean plus 1 standard deviation, so that would take us to 75 pounds. So therefore, 68% of the children would have weights between 55 pounds and 75 pounds. Okay. Part B, we're switching out 68% for 99.7%. So that means when we do our calculation, we have to change from moving by 1 standard deviation to 3 standard deviations. So our lower limit would be the mean minus 3 times the standard deviation. So we'd have a lower limit of 35 pounds. The upper limit would be the mean plus 3 standard deviations. So that would give us an upper value of 95 pounds. So therefore, 99.7% of the children would be expected to have weights between 35 pounds and 95 pounds. Our third question is a little bit different. In a sample of 200 children aged 10 years old, how many will have a weight between 45 pounds and 85 pounds? For this question, we have to think backwards and think about what percent of the weights is represented in the range between 45 pounds and 85 pounds. So since our mean is 65 pounds, our upper limit of 85 pounds is equal to the mean plus 2 standard deviations. The lower limit, which was 45 pounds, was the 65 minus 2 standard deviations. So that means, since we're at the mean plus or minus 2 standard deviations on either side, 45 to 85 pounds includes 95% of the children. We could set up a proportion or some other method to do our calculation. Here, if we set up a proportion, we could set up 95 out of 100 equals how many out of 200. And so our answer is that x equals 190. Therefore, 190 children would be expected to have weights in that range. Okay, I'm almost out of time for my screen capturing. I'll post this and then there'll be a short second post with example 4 in it.